The following content has been provided by RWTH Aachen University.
This is designing interactive systems. The most important thing to remember from this class is the jump page URL that is at the bottom here. This is the homepage of our institute, hci.rdhachen.de/DIS. So make a note of that URL because this is where you'll find the answers to all those questions you might be having later, where we gather all the materials, slides, pointers to the videos, announcements, etc. I'll tell you just a couple words about where I'm coming from. I studied computer science myself, then went on to do a PhD in it, and started to focus on things like design patterns, interactions, multimedia. So HCI has always been sort of the field that I got most excited about in computer science. I then did an assistant professorship at Stanford, moved back from Silicon Valley then to ETH Zurich briefly, and then have been a full professor here at Aachen University since 2003. The things that we focus on in our lab, I'll talk about a couple of sample projects later, are how to make it possible in new ways for people to interact with technology. Building new user interface technologies, trying out new techniques, evaluating them scientifically, and hopefully improving usability of technology for folks. All right. Here's our two PhD students who are assisting with this class, Ricardo and myself. You want to just get up so everybody can see you guys are physically here. So these are the people that will answer your questions. Send them emails if you have any questions about the class. Don't send them to me. I do get a lot of emails, and I probably won't be able to answer anything as quickly as these two can. So, to make this super clear, since we're all computer science students or with a background in computer science, here's a handy little flowchart how, if you have a question, what to do, all right? So, you have a question. You ask yourself, well, is it something that I feel comfortable sharing in the forums? Usually it will be, right? It will be something like, when is the assignment due, or where do I find the link to these papers again, et cetera, et cetera. Anything that you think is not going to be incredibly personal and nobody else can possibly know about it, that, by default, should go into the forum, right, on the RWTH room. Now, if it is something that you're really concerned about, that you definitely don't want to see on the forum, and you're sure nobody else will need that information, then you can send an email. Put the prefix DIS1 in front of it so that Marcel and Ricardo can filter for these things quickly, and that will take care of any personal questions. Now, doesn't usually happen ever, but if you do have something you can't work out with Marcel and Ricardo, they're really nice people though. But if there's anything, of course, feel free to reach out to me. Okay. All right. So the other solution is the beauty of presence lectures. You can just stop by after the lecture. Usually we'll be hanging out here for a couple more minutes while we're tearing down, and you can ask your questions then. Okay, that's another option. Okay, so human-computer interaction. What is that about? What is the discipline of HCI? Well, it's about user interfaces, like this really bad one, for example. This is the one that I found by googling bad user interface a while ago. This was like the #1 hit on Google for that kind of bad UI. So I'm not sure whether people were happy about that kind of Google ranking, but there you go. So this is apparently badly designed, right? It's like way too much information. It's not structured in a way that you can easily parse it. The color coding is not clear what it means. It's highly confusing, so badly designed. But what's the big deal? You might say, well, people are going to take a little longer to learn this and to use it. So what's the big deal? Well, the big deal is that you get unhappy users, right? And happy users has effects on a variety of levels. First of all, of course, it means that people take more time to do their tasks. They will make more mistakes. So you will see errors that slip into people's work or play or whatever they do, whether it's personal or work related. But also then there are some more subtle effects, but probably the more devastating actually. You will see user satisfaction going down with the product or the app that you wrote. And that means, in a business context, speaking in a business context, you are increasing the total cost of ownership. The total cost of ownership is a very simple concept that says you can buy a very cheap PC for like a couple $100, but if you then spend 10 hours each week fixing it, you are sinking a lot of more money into that product and into it. So a bad UI will increase the total cost of ownership of any software solution in the business sense. But also, especially, this is especially relevant for countries like where we are right now. In high-wage countries, this is an incredibly big part of the business calculations. But also, if you're not in a business context, if you're writing just an app that you are selling to people to enjoy, I don't know, to like track their water intake over the day or something, if this has a bad UI, then you won't grow any customer loyalty, right? People won't actually get attached to your application and recommend it to others, and they'll probably hop off the bandwagon next time something better or better design comes around. So we want to avoid this, and this is an example of an interface that also maybe not the best designed one in the world. The point here is user interfaces are not just the things that you put on screens on a smartphone or a tablet or a PC. This is also a UI. Right? Even this door has a user interface. It's something in the handle to open and close it. So user interfaces are basically something that surrounds us everywhere. Right? And my secret goal of this class is you're all going to get brainwashed a little in this class, right? So be ready for this. And when you all leave this class, you will all be really, really good at complaining about bad user interfaces. So you'll all be nitpicking and saying, this wasn't designed well and so on. But hopefully you'll also be able to see when things are designed well and be able to tell why they're designed well. So that's our goal here. The beauty of learning about UI is that it applies to technology in all kinds of shapes and sizes, and it also is knowledge that will last you for a long time. Unlike the things that you might learn about the latest software frameworks, which are usually probably out of date by the time you leave university, this stuff stays around for a long time because, believe it or not, but our brains haven't been updated to version 2.0 yet. Right? We're still running around with essentially the same ones that we've had 50, 100 years ago. And so anything we learn about how people react to technology, how they best work with technology, is something that you can hold on to as knowledge and as expertise throughout your career. But, so this good usability, if that's all great, and we're making the world a better place, as they like to say, but it also sells. I just want to show you a very quick example of why that is true. We, by the way, just a quick check. Can you guys hear me okay in the back? Yeah? All right, good. Here's an example. In 1996, Sony introduced a DVD player. And that was back in the time a revolutionary device. And it sold 350,000 units in its first year. And that was a record by that time. Nothing else in terms of consumer electronics had ever sold that much. In comparison, the iPhone that came out in 2007 sold 1 million units in its first quarter alone. Now, this is maybe not a fair comparison, right? When the DVD player came out, nobody had DVDs, right? So getting a DVD player was kind of, what am I going to do with this? Whereas when the iPhone came out, there was already a mobile phone network. You used to see turn on and immediately start using the infrastructure that had been built around it. No apps, right? App stores didn't exist, but this thing worked really well as a phone and as a mobile web browser and as a music player. So maybe that's not a fair comparison because the ecosystem isn't there for the DVD. But the really surprising number, to my mind, was when the iPad was released a couple years later, in 2010. It actually sold 3 million units in its first 80 days. That's even less than a quarter. And what's weird about that is there was no killer app. And this thing wasn't cheap. And when you talk to people, so why are you getting an iPad? They're like, well, I don't know exactly what I'm going to do with it, but I want one. So what had happened there was that since the iPhone had people had been exposed to the iPhone for a couple of years, and they had seen that its usability was really good. So they actually transferred that understanding that, okay, that seems to be a company that knows how to do usable technology, that actually transferred over to the iPad. So the iPad got a lot of advanced credit, and people, buying it, even though they didn't quite know what to do with it really, but they assumed it to be good. And of course, there are other things in there. There's hype. There's, Apple has a well-oiled marketing machine too, right? All this is there, and they do good jobs in industrial design, product design, but also the fact that you had a usable product really sort of gave a forecast on the usability of the next product. So that's a little bit of the business case of usability. It's much more to say about this, but this should suffice for now. I want to give you another view on what human-computer interaction and usability is from a disciplinary view, and from a view where I can tell you what we're teaching in this class. This is an overview of what human-computer interaction, the academic discipline that is all about usability and people interacting with technology, what that discipline actually covers, and how our classes fit in there. So, of course, what you would expect in an overview of this discipline is humans and computers. Duh, right? That's not very surprising. So, as you can see here, for the humans, we are interested in things like how do humans actually process information, how do they communicate among themselves, but also, especially with their environment in general, and technology is part of that environment. And on the other side, of course, you have the computer, things like computer graphics, or how are dialogues structured, and how do you differentiate between different technical interactions. And around these two things, humans and computers, there are two other areas. One is to understand that actually you need to understand not just the fundamentals of human psychology to do a good job at designing interfaces, but you also need a process to work out for each project that you do, in each app or design that you do, what the right solution for that particular situation is. I like to think of good usability as sort of a two-stage rocket, right? Stage one is the stuff that we're going to be covering in the first couple of weeks here. Fundamental psychology rules that always apply and that will help you no matter what to do a better job at interface. Right? They apply to any user, any task, any context. The rest of it, though, the other 70% of the doing a good job in the user interface really mean that I can't give you the answers on what the right solution is. You need to find them yourselves. But how to find these answers needs a certain process of user-centered design, and that's what we will be talking about. You could also call this design thinking. This is kind of the thing that helps you to understand really what users need and figure out together with them how the product needs to look to support their needs optimally. So around humans and computers, we have a design process, like a development process, right? With different approaches on how to do design, how to do prototyping, and how to do evaluation, and about example systems. And again, example systems and design approaches is also something, all these things, we will actually be covering in this class. And the later part of the class, the last third, if you like, is really about the evaluation techniques and prototyping techniques. So what you're seeing here is there's another area out there, which is about use and context. People interact with technology not in isolation. You're not in a black box, just you and your smartphone. There's other people around you. You are in maybe a noisy environment, or you're walking across the street while you're using your phone. Others are talking to you, interrupt you. The messages you're sending, go to other people who answer back. So there's always a big social context of any interaction. Don't assume otherwise, because then you're just kind of lying to yourself. So any interaction is happening in a social context, and that is also an important topic of HCI, but one that we won't be going into in depth. There's great classes on computer-supported collaborative work by Prince, for example, colleague here at Haptic Output, and also at the Farmer. So what I'm trying to show you here is this is HCI as a discipline, okay? And the red circles here indicate the stuff that we're covering actually in DIS1 in this class. This right part here, implementation techniques and tools, and dialog techniques, dialog genre, dialog architecture, input, output, device technology, that's all something we will be covering in a follow-up class, designing interactive systems 2, surprisingly. We're not going to go deep into computer graphics. We'll touch on a couple things that are especially relevant for HCI, but if you really want to dig deep into computer graphics, of course, there are excellent classes that my colleague like colleagues on. And as I said, CCW here if you're interested in this. So let's break down the class in a different way to give you an idea of what we're going to be doing this semester. The class falls into basically 3 chunks, and each of these chunks has a different focus. The first focus is on the human, kind of like the left-hand side of things that you just saw on that graph. So it will talk about how well can people actually remember stuff? How fast can they react to things? How long will they remember something when I showed it to them? Because that's kind of important. If you rely on the user remembering something in your UI, then you better know what the human's capability are to do that. We will also talk about different models of interaction. So what are the things in objects around us that make us use them in a particular way? What are the aspects of product design, of interaction design, that influence how we approach a piece of technology? I pick up a device like this one here. How do I know how to use this? And what is it in the device that tells me how to use it? So we'll talk about these things, affordances, matter, trains, different types of knowledge, like knowledge that is basically encoded in the device versus knowledge that I need to have in my head to use things, and of all the many different mistakes people make. Because guess what? Making mistakes is human, as they say, and that is especially important and relevant for HCI. We need to design so that people can make mistakes with these things without breaking anything or losing any information, etc. And that will wrap up basically with a couple of design principles. We will also have a nice little class on visual design, so I'll give you guys a 1 session crash course on how to do a better job in graphic design for not just graphic user interfaces and laying out your app, but also it'll be useful for your slides, your posters, your images in your thesis, whatever. Whenever you need to communicate something in text and graphics, these things will be very useful. So we'll all be becoming kind of designers a little bit, but don't get out of that turtleneck yet. It's really just a crash course. The second part of the class, then, will, like I said down there in the graphic, the second part will look at the history of HCI. See, we said down here that you need to look at example systems and case studies to understand how successful user interfaces have been built. And to do that means that you need to take a look, kind of like an architecture class, at sort of the great masters. Like you need to understand what are successful user interface designs in the past, how did they come about, what did people do great. So that's going to be a very terse and brief history of HCI with some kind of looking back at the great architects, if you want, of HCI and the steps that took us to where we are today and where we might be going tomorrow. So we'll also be looking at some future visions of how we people are imagining the future of HCI. This will wrap up with a brief review of how technology is being designed and how it evolves over time, and what kind of lessons we can learn. The third part of the class is then the development process. This is when it really gets very hands-on, because what we'll be teaching you there is basically the sort of the components of design thinking, right? The components of iterative, user-centered design, which means you're going to learn how do I observe people to understand what kind of issues they might have with the technology. Right? If people are using a ticket machine, at the train station, what are they struggling with, and why are they struggling with certain things? What things actually happen there? To develop a keen eye for usability at this level. Then we are going to get into ideation techniques. How do I create new ideas for a user interface to improve the state of the art? We're going to talk a lot about prototyping. Prototyping is going to be a major part. How do you create a prototype of your user interface. And I hate to break this to you, but this means not writing code. This is not a class where we will be coding a lot. This is a class where we will try to really emphasize the early part of designing a user interface, where it doesn't make sense to write code. Why? Because writing code is expensive. Right? Developers are expensive. Making mistakes in code and fixing them is expensive. It takes a long time to correct something, compared to me just scribbling a square for a window on a piece of paper and showing it to a user, and they say, no, I want this to be in 2 windows. And I just throw away the piece of paper and sketch a new one. This is much faster and gives me the right kind of feedback. So we will be talking about paper prototypes. We will also be talking about software prototypes, but these are going to be prototyping tools that are not your final development environment, not your Visual Studio or something or Xcode, but actually tools designed for the job of prototyping, quick iterations in the user interface. And why are you building prototypes? Well, to test whether you are on the right track, right? So we're going to talk about how do you evaluate prototypes with users. How do you figure out whether what you design is actually what people need? We're going to learn about a couple different techniques there that will help you evaluate your prototypes with users, and even without users. There are some evaluation techniques where you don't actually need users around, and you can do this in your team yourself. We will wrap this up then, this last part of the class, with a couple notations, because once we figured out what the interface is supposed to look like and how it's supposed to behave, we somehow need to communicate that to the rest of the team, like the developers, for example. Maybe we are the developers ourselves, but we need to write it down somehow, right, to remind ourselves or to communicate our designs. And that requires special notations. Just as we have programming languages to code algorithms, we need design notations to write down, for example, under which circumstances a certain screen in an app is supposed to move to a different screen, how fast that's supposed to happen, what the conditions are, etc. All right, this class actually has, for the first part here, the human, so to say, it has a textbook. And that textbook is called The Design of Everyday Things. It was written by Don Norman. Originally, it was called The Psychology of Everyday Things, and then he discovered that nobody buys a book with that title, and we renamed it to Design of Everyday Things. It has been probably the single most best-selling book, on HCI for a broader audience. This is not a complicated text, I would say. It is a text that is very rich in examples of how our everyday environment actually makes us behave in certain ways, how everyday things are designed to be usable or not. So it talks about all the struggles that we have in everyday interactions. And this is a book you need to get for this class. So if you're taking this class, get this book today. You can get it as an ebook, you can get it as a paper book. But you'll definitely need it, and it's the book that we will tell you each week which chapters you're supposed to be reading off that. There's another book called Human-Computer Interaction by Alan Dix and his colleagues that we also recommend. It's quite a volume, but it is an excellent all-in-one sort of book on HCI as a discipline. It talks about much more than what Norman does. Norman is really mostly there to shorten your sense of good design in everyday user interfaces. Right? This is sort of the icebreaker, so to say. And then the other book is taking a much more all-encompassing academic approach and really tells you about all the different things that need to be happening in the design process, etc. We will be having a few chapters of that second book as PDFs available on L2P. Or not L2P, I guess these days. It will be Moodle Artificial Online, somewhere behind the paywall, basically, right? Yeah, there you go. So these books are still going to be very useful to you if you want to get into the discipline. All right. Let us take just a minute to give you guys an idea of why we're doing this. And I want to give you a very brief idea of what our class, our chair, the Media Computing Group, is offering beside this class. so that you understand what you could get into as follow-up class and how this fits in. The classes that we offer are for bachelor students. We have multiple media madness and human interaction, a software practicum and a seminar, a pro seminar that we offer in the undergraduate education. And then we've got Design Unit Systems 1, which is sort of the foundational class that we recommend everybody to take who wants to get into interface design, usability, human-computer interaction, this kind of stuff. It will be followed in the summer by Design Interactive Systems 2, which is the more technical class. That's when we will actually start looking at how does, clicking the mouse on your computer, on your desktop, how does that actually make its way into the computer, into the operating system? How does that bubble up? And how does the computer figure out which window was hit, which application it belongs to, and what is supposed to be happening in response? DIS2 is much more about coding. We are actually going to, in this summer class, we're going to be building user interfaces, simple kind of like Hello World style user interface, in a whole variety of different user interface toolkits. Desktop toolkits, mobile toolkits, post-desktop designs for stuff like physical computing and embedded computing. So it's a pretty technical class, a lot of coding, and it's sort of the accompanying package to DIS1. I want to make sure that you all understand first what makes a good user interface before you then go out and actually use tools to create. We also have iOS application development. That class started yesterday. If you missed the first class, then I think you have a few more hours to try to sign up for it. Very limited seating in that class. This is a class that teaches iPhone and iPad development. We basically go through these the development environment. We go through the various patterns that are being used in mobile development. And so, on the one hand, yes, you learn how to write iOS apps, but it also is a great way to understand how a fairly modern tool is structured these days. Because if you end up, you're a PH Aachen student, so you're not just going to be writing apps, you're probably going to be the architects of future IT infrastructures and future IT user interface toolkits or operating systems maybe. And so these kinds of things, learning how a modern toolkit is designed helps you to transfer this knowledge to your future work. And it's also a good class to learn about mobile development as opposed to development for the desktop device. Then we have current topics in HCI. That's a research class. That is a class that definitely is for people who are interested to do their thesis in, with our lab, for example. And there you learn basically two things. On the one hand, we talk about in depth how HCI research works, because research in human-computer interaction is actually a bit different from most of the research that you do in other areas of computer science. The reason for that is that we are not just about building artifacts, like developing a new algorithm and testing that it's faster or something else, but we need to always have an empirical validation. So it's a lot about study design. How do you make a user study, so for example, so that it is fair and is correct and is valid, what you find out for it. How do you balance your groups? How do you do the statistics for it? So yes, all of that stuff that you loved about your statistics classes that you took as an undergrad are going to be coming back in this. Because HCI is actually a discipline that is sort of, it has a lot of computer science in it, but it also has a lot of psychology in it. And with the methods that come out of the more lab-oriented cognitive psychology. And then there's design as the third discipline. We're in the intersection of all these three disciplines. So anyway, that's what you learn in current topics in HCI. And then we actually give you an overview of current topics in human-computer interaction. And that's also a great way to learn about research that we currently find exciting, that maybe we are working in ourselves. And so if you're looking for a thesis topic, current topics in HCI gives you a little sort of catwalk where all the PhD students also present their specific area of interest to you and share some of their current work that they are doing that they are finding exciting. So it's a great way to find a PhD student to work with for your final thesis. Well, and then we have the post-desktop user interfaces seminar and the media computing project. These are the seminars and practical labs that we offer in the graduate level. All right, a couple examples of the kind of stuff that we end up doing. This is ARPen. It's a little tool that lets you actually design things in midair. Why are we doing this? Well, 3D printers are great, but how does somebody get their idea that they have of an object that they want into the computer in the first place? I can Google for it, or I can look it up on Thingiverse or some of those platforms that have 3D models. But if it doesn't exist there, and I need to design it myself, then how do I do it? And so learning AutoCAD is one option, but that's kind of not for everybody. So we were looking at alternative ways for people to just sketch something in 3D, like they would on a piece of paper in 2D, and then just make that a 3D model that they can then further refine or work with. And this is the very first exploration of that. The ARPan app is actually in the iOS store. If you happen to have an iPhone, you can download it and play with it yourself. You just need a little printed out QR code, and that will become your pen with which you can then draw in 3D. Holding your smartphone in one hand and your cardboard pen in the other hand, you can kind of doodle objects, and this is kind of what it looks like. You're drawing things like that in space, and these things then actually can be printed directly on a 3D printer if you want. A second example of the, or maybe I should say, what I really find exciting about this kind of research is that we are learning something about a new interaction that people haven't been doing before. Because here I am with this pen in my hand, in one hand, and with my phone in the other hand, and now I'm looking at my pen through my phone, kind of with this camera, and that's a very unusual thing to do, actually. You are seeing a real scene through your eyes, and then you're seeing the virtual screen, the virtual scene through that screen that is kind of like at an angle to you, but it's also at an angle to the object. And you're almost like a fly with facet eyes, so you're looking at something from two sides at the same time. Or you could say like you're like Mad-Eye Moody from Harry Potter, who has their eye floating around anywhere they want, right? So you got this additional camera on the scene, and through that you're seeing what you're doing. How good am I at judging distances? How good am I at hitting a particular point in an object, for example, in a 3D scene? We don't know. Right? That's fundamental questions of cognitive psychology that we don't have answers to right now. But they're on the table, right? Because these technologies, these interaction techniques are happening. So that's what I like about this research, that we learn something about fundamental truths about how people interact with new kinds of technology. Another example of our research, and that should be enough then, is you can create output to the user in a couple of ways, right? I can show something on a screen, use the eyes. I can play back some sound, that's use the ears, or I can literally tap them or touch them, create some haptic output. When your phone vibrates in your pocket, that's haptic output. But there are so many different ways in which we can sense haptic output as people. Right? You can sense whether somebody does this on your arm, or whether they tap you, or whether they pinch you softly, or whether they do this kind of movement, or roll something over your skin. All this is something that we can feel as users. But computers aren't able, and technology isn't able to do that. Like your smartwatch cannot do all these things today. But what if it could? Right? So researchers have been playing around with this idea of different kinds of haptic output to the user on their skin for a long time. But it usually involved really bulky, motors and servos and whatnot, very complex technology, and they were all one-off setups. And they were also pretty noisy. They were like click, click, click. And so we designed a new way to do haptic output on the skin using shape memory alloys. That's a weird material that will actually spring back to its shape when it's exposed to current, because that heats it up. So it will kind of remember its prior shape. And so what we were able to do with this is create different kinds of effects, like what you can see here on the skin. This softly contracts and gives the user a soft pinching motion, or this will create more of a sliding motion towards one edge, or tapping them in the middle. And all these different, here's a little bit of a slider. And all of these are using the exact same, very simple, completely silent technique using these shape memory alloys. All right, enough of our projects. Here's a project students have done. This is taken from our undergraduate bachelor project that is aptly named Multimodal Media Madness. Each year, students go crazy on an idea. For example, I'm a big fan of escape rooms, and I love steampunk design. So one year we said, okay, why don't you guys all go out and just build some kind of escape room riddles in a Victorian kind of steampunk style. So of course that requires much more than writing code. It requires you to think of a good user story, of a good interaction, of an interesting riddle, and then you need to build that in code, but also in electronics and some hardware. We have the facilities at our lab with 3D printers and laser cutters and whatnot to do all this, and this is an example of a safe that a couple of students built a couple of years ago in this lab. It's basically a cooperative game to open the safe because each side has one player, and you need to actually solve puzzles by describing the blinking keys or identifying the correct pitch of a note that you're hearing together in order to open this safe. So it's a fun little example of a project that people were able to build within a semester. All right. Two more things that, while we're here, that we want you guys to be aware of. There is a monthly maker meetup. The next one is happening on October 19th. If you're interested in that, this is a monthly get-together that I've been organizing for a long time, not just for students, but also for people from the area who are interested in hacking with technology, building electronics, doing art projects, interactive exhibits, whatnot. So that's the Aachen Maker Meetup. And the second thing that you might be interested in, we have also a monthly meetup of people who are developing on iOS and macOS. Again, you get a lot of people there who are not from the university too, so it's your contact to businesses and developers in the region that are excited about developing for these platforms. All right, now we're going to get to the course structure next because I want to give you guys a rough idea on how this class works. The course structure is that we have a lecture, and that will be going on the entire time. Right? Each week we'll have this kind of class. We'll have a couple of in-class exercises each time too, to give you guys a chance to participate in the class and wake up and turn on your brains and go into active mode. And so I highly recommend coming to the class rather than consuming it online via the recording, because you're going to miss out on the interactive parts. You usually need to cut those out of the video because they don't really make sense watching them online. Then we have the lab that's going to be happening where you turn in assignments in groups of 3, and these basically, during the lab sessions, we'll be discussing the contents of the assignments and, of course, the lecture, any clarifying questions you might have. We show examples, we go a little bit deeper, give you kind of additional examples to better understand the lecture content. So not new lecture material, but better ways to understand what we think happening in the lecture. The assignments are all group-oriented because I think it's really important for you folks to work on teams and understand how to do this and how to work on projects. And once that's done, we have a midterm. Right? That's going to be happening on December 6th. We have the midterm during usual lab times. And so the midterm is basically your first part of collecting part of your grade. In fact, the very first part of that is already in the assignments too. After the midterm, which is kind of like a mini exam, we then move into a UX project. That's going to be happening in the second part of the class. This is where you basically create your own project in groups of typically 6 people, and you create a final showcase video of your project that you did, and you present that to everybody in final presentations. After that, we have a final exam, first and second dates. Currently here, February 10th and March 17th are the dates that we are planning to have those exams. This may still change, and we will certainly let you know if it does. But for now, mark your calendars for those dates. Don't go on a skiing vacation during that time. All right. Now, here's the feedback that I get almost every year for this class. 2 things that students usually say. They say, "Boy, this was a lot of work." And the second thing we usually get is, "But it was totally worth it." So this class is not going to be a low workload, right? This is going to require continuous work from you throughout the semester, working in teams, teaming up with your teammates, making sure that you get your assignments and that you stay on top of the material, that You actually do the reading assignment. So this is not a class where you can go like, woo, I'm going to relax and have parties, and then 72 hours before the final exam, I'm going to cram all this stuff into my head and not sleep and then write the exam. Not going to work with this. Okay. We all know that that's not a healthy way to study, and that the better way to do this is to study continuously throughout the semester, right? So we want to support you in doing this, and this means that you can actually collect most of your grade already before you walk into the final exam. The grade distribution is like this. You do your assignments, they will make up for 20% of the final grade. The midterm exam will make up for 25%. The final exam will be 35%, and the project another 20%. So as you can see, all these things, the day you walk into the final, you basically have 2/3 of your class, of your grade already in your pocket. You don't need to worry about it anymore. So when all these other classes are piling up and you're crunching for all of those, hopefully DIS1 is not going to be one of them because you've already done the studying, you've prepared for your midterm. That's a great way to review the first part of the material. And by sticking with us with the assignments, you won't have this gigantic, massive stuff to do at the end of the class. All right. To pass the course, I should say this very clearly. You have to fulfill two things. Right? You have to have a 4.0 in the final exam. So you need to pass the final still to complete the exam. And you also need to have an average grade that is a passing grade for all of this. So two conditions here that are linked with an and, right? So both of these things need to be true for you to pass the class. All right. How do you sign up for this class? It's limited to 120 seats. As you can see, I think, from the way we teach this, it's an unusual class. I know this. And why is it unusual? Because HCI, it's not something where I can just give you a textbook and tell you what you need to do to talk to a user to figure out what they need. You actually need to go and talk to a user and watch them and observe them. Right? So a lot of this stuff is hands-on training that needs to happen, and that requires a lot of us, helping you, reviewing your designs, giving you feedback on them, and this is why we need to limit the class to 120 folks. In order to get into the 120 seats, or to maximize your chances of getting in there, you need to register via RTH Online. Who has already signed up in RTH Online for the class? Right, that's the vast majority. If you want to take this class and you haven't signed up, do that right now. It's not first come, first served, but you need to be in there to be considered. Second thing is, you need to send the declaration of compliance to us today. Again, who's already done that? Look at that. Yeah, almost as many hands. So again, if you decide to take this class, and it's not an easy one, you need to do that today. Did you have a question?
Yes, on the web page it says that the email subject should be this 22 DOC year. Not for long.
We're going to fix that right now.
Both are fine. Both are really
yeah. Thanks for pointing that out. Those are not questions, right?
Yeah, so I looked at the website and the PDF file should be named DIS1 line also with matriculation number.
Yeah.
However, I already did send an email on the first day the registration was open and the requirement was 4. Is that still okay? Or?
Yep, that's still okay. So if you already sent it to us, don't worry about it. So basically, I just received like 50 of them and renaming them by hand took me a little long.
Okay.
So this is why I put it there, that it would be nice if you already named it for us. But if you already send it with the whatever name, then that's fine too. So don't worry about it.
All right. So that's the second thing you need to do. Send that today. And any, do we have a time constraint, Marcel?
Yes, the things will close, the registration will close tomorrow, and we will register everyone on Friday.
Okay.
So on Friday you will know whether you're in the class or not.
Right. That's important for you guys to know. Of course, you want to plan your semester, so we will let you know those ways. And again, here's the note: like if you are a Russian student, anybody who cannot register via RTH Online, talk with Carl and myself, and know include your matriculation number and full name from your official email address and everything. So we're now going to start with the actual content of the class here for you guys. And what we'll begin with is this first part of the class, which is about the human and some basic cognitive psychology for you folks. Really on a very fundamental level, on an engineering level, we don't want to understand the deepest secrets of how the human mind works, right? That's not the goal of this class. We want to get to models that we can use to predict how well the user interface is going to work, how well the user is going to be able to use a particular technique or technology. And for that, there are a bunch of models. Let's start with a very simple one that's been around for a while, but is really helpful to predict fundamental human performance parameters. The model is called the Model Human Processor. This was part of a book by three folks, Hart, Morin, and Newell. They published this in the 80s. And it was the first book that actually took results from psychology and applied them to HCI. So it took this whole bunch of knowledge from an existing scientific discipline and basically said, how is that going to be relevant to human interaction? So, however stupid an engineering model is, as long as it gives me useful predictions, it's good enough. Right? We don't care to understand exactly how the human brain works. We just want some ways to predict performance. So, the Model Human Processor is a simple engineering model of that kind, of how humans process information. And this is the overall structure. It has 3 processors, and each processor has associated memory. As you can see here, there's a perceptual processor, there's a cognitive processor, and there's a motor processor. And this guy here, this bubbly head guy, is currently looking at a screen, seeing maybe something appear on the screen, and is pressing a button in response. So something very, very simple. For all the numbers in this model, you don't need to go into the details here right now. We'll cover this one by one. There are actually a variety of numbers. The average that humans have, but also a typical slow performer, middle performer, and fast performer. Right? So there are actually 3 kind of different points here, which already indicate to us that, of course, not all humans will perform the same. We need to live with quite a bit of variance in this and need to design for these variances as well. We're going to do the first in-class experiment now on this about the perceptual processor. This should be fun. So we'll work in pairs of 2, and so just find the person sitting next to you, or maybe with a bit of distance, so you may need to scoot together for this. And I would like one of you folks to read the text that we just handed out from experiment 1 to your group partner. And the other person just needs to do the following. While you are reading, you turn towards the other person and look at your piece of paper, but so that the other person can see your eyes, okay? You can leave your mask on because you don't need to understand what's being said. What I want you to do, the other person will watch your eyes and watch exactly what your eyes are doing, what your pupils are doing as you are reading. Do that just for a couple seconds and then switch roles so that the other person also gets to see that. All right, go ahead. Can you raise your hand? What did you notice? Anybody? Yeah, go ahead. Yep.
So the eyes were moving side to side, and when the person is actually reading, so from left to right is slower, and from right to left, so when you go, you're giving the line.
It's faster, right? Yeah, that's right. So they move from left to right. Anything in more detail there? Yeah, go ahead.
They don't glide, they move in steps.
Right. They move in steps. Anybody else notice that? So the eyes don't go like a scanner, but they actually go like doop, 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 like this, right? So that's a typical eye movement that's called saccades. And these saccades are a fundamental feature of how the human eye works. It basically looks at a blob of text, focuses on it, processes it, and then moves on to the next one and focuses on that. This is how our eyes work. So the perceptual processor is modeling what the eyes are doing. And these saccades that you just saw actually are fairly slow. They happen at a speed of roughly a quarter of a second, right? 230 milliseconds on average for doing this. So roughly 4 saccades a second you're doing while you're reading. And these eye saccades are actually the reason why you cannot read text arbitrarily fast, right? So since your eyes need to look at a
chunk of text, and they can only do that 4 times a second, and you can't take in like a whole page of text in this quarter second. It has to be within your focal region that you can actually sort of see at high resolution. That limits actually your reading rate to roughly 13 characters per second is what you can actually see in terms of how much of your eye can actually see at this high resolution, and that will translates, you can figure it out, to roughly 600 words a minute that you can read. So the area of actually sharp vision in your eyes is extremely narrow. It's only about 2 degrees. That's not a lot. And this is the explanation why there is this very narrow area that your eyes can actually focus and see text sharp enough to make sense of it. And then you move this sort of focal area from block to block really quickly. And that is basically the reason why you cannot read any faster than that. Or can you? Does anybody have an idea of how you might be able to read faster than that? Yeah? Mm-hmm.
I think like when you learn like how to read fast, you just need to like kind of follow the ad like in the middle like this, like in the middle of the text.
Okay, but yeah, okay, so but then you are not actually reading the other text, right? There are ways. Yeah. Yeah. Other ideas? Yes, please. Mm-hmm. Yep, so that's very close. There's actually a technique that does that. Does anybody know what that looks like? There, yeah, go ahead. Yeah. Exactly. Right. Exactly. So it's this rapid presentation of words in the same place that computers can do, right? Then your eyes don't need to do saccades. They don't need to move. Your focal area stays where it is. And then you can actually read faster than with your normal way. So that's an interesting way to kind of like, cheat biology and not use that relatively slow part of the visual apparatus, and that can speed up your reading time. It's called Rapid Serial Visual Presentation, RSVP. All right, so this is what we basically know about how, on the very fundamental level, we take in pictures, right? That's what we're doing there. So, but there is another thing going on here. So eye movement, this is what I talked about so far here, is about 230 milliseconds per saccade, although it ranges widely, as you can see here, 70 to 700. And then things enter the perceptual processor. And that has a different processing time, not the time from the eye saccades, but 100 milliseconds. Let me talk about where the 100 milliseconds are coming from. If you have any experience in photography, then you know that if you take a picture, you're exposing the film or the sensor to light for a certain time, right? For a certain duration, the exposure time. And anything that hits the sensor during that time basically gets integrated up, right? That's how photography works. Well, your eyes actually don't work that differently. When you look at, here's a nice little experiment that you can do. We can't do it here, but if you did that and you showed somebody a very brief light flash, a single light flash at a certain intensity, like this blue box here, right? And after that, you showed them a longer flash that takes twice as long, but it's half as bright. People couldn't tell the difference. As long as we are inside a time window of 100 milliseconds. You could think of that a bit like the exposure time of your eye's retina, basically. It gets even weirder. If you show somebody 2 light flashes, one after the other, with a break in between of half intensity, it will also look to that person exactly the same as this single light flash of a higher intensity. Okay? So what's happening here is clearly the eye is also integrating up the photons hitting the retina during that 100 millisecond time window. It's more of a sliding window. It's not that strict, serial thing, 100 milliseconds, 100 milliseconds, like you would have in a camera. But that is basically giving us the explanation of why the perceptual process that we talk about here is 100 milliseconds. So what that means is that basically when we talk about the now, philosophically speaking, what's happening right now is actually, at least as far as your vision is concerned, happening within a 100 millisecond time window. Right? So if, for example, two lights turn on and they turn on within a 100 millisecond time frame, then you probably won't be able to see that there was a latency between these two, like they were not turning on at the same time. And that is a reason why this 100 millisecond number will come back again and again for us as a deadline that we need to keep in mind when we design user interfaces. This fundamental truth here about human perception and especially how the eye works is the foundation of what's called Bloch's law. So Bloch's law says that the response that people perceive is simply the intensity times the exposure time. Or if you have a more complex curve, it's basically the integral under the curve of what the exposure was over a certain time. And what's interesting is that all these three things will look the same to the user as long as it happens inside that 100 millisecond time window. That's important. Of course, if I show you two flashes, half a second apart, of course you can tell that there are two flashes, but not within the 100 milliseconds. All right, so I'm going to show you a second experiment now. And that experiment will show you basically two, you can think of them as billiard balls, right, colliding. So there will be one billiard ball approaching, a white billiard ball, and it will hit the second billiard ball, and the second billiard ball will take off, all right? And I want you to pay attention to this and judge whether you think there is a delay between the first ball hitting the second one and the second one taking off, or whether there is no delay. Right? Is it immediate, like in a physical situation, or is there some kind of pause in between the one ball hitting and the other one taking off? Okay. So here's the first example. All right. Okay. So let's do a simple show of hands here. Who thinks there is a delay between these two? Then raise your hand. Okay, that's about 10, 15. Who thinks there's no delay? Just to see if everybody's awake. Yeah, majority thinks there's no delay. All right, let's do another one. I'll show you a couple of these. Here's a new one. Let me play this one. So it's looping, right? It's always only about the contact point when the one ball hits the other one, and then the other one takes off. Again, who thinks there is a delay? About maybe 25. Who thinks there's no delay? All right, majority thinks there's no delay. Okay, but a couple more people think there is a delay. Let's look at another one. This is, there we go. All right, so who thinks there is a delay between ball arriving? Everybody. All right, nice. Here's what you just saw. Version A had no delay, 0 milliseconds between one ball arriving and the other one taking off, right? And apart from a few people, everybody thought this was happening immediately. The last one I showed you had 100 milliseconds of delay, and everybody saw the delay, right? You were able to tell that there was a latency happening. And in between, we had this second version here, which had 50 milliseconds of delay, where some people already felt it was a bit sticky, and other people thought, no, that's still an immediate causality, right? This ball is really taking off as soon as the other one arrives. And that's perfectly normal, right? It's a statistical distribution. Maybe some of you guys, already had 2 cups of coffee this morning, and so your brain is on high gear and is actually aware and is able to tell these things apart more clearly than other people who maybe partied hard last night and aren't quite there yet. So that's perfectly normal. Okay, there will be interpersonal differences on this. If you run this experiment with a lot of people and a lot of different delays, this is what you get. And this is a graph taken from the original work that Cartmore and Newell were publishing in the 80s on this. So here's the delay before the second object moves, right, goes anywhere from like basically 0 or 10 milliseconds all the way to almost 200 milliseconds, right? So 100 milliseconds is roughly in the middle here. And then we can see how many % of the participants in the experiment said that there was immediate causality, meaning there is no delay, right? That's the dotted line. How many were delayed causality, felt like something is going on, and how many people said these events are completely independent, right? So as you can see, as soon as you go beyond roughly 50 milliseconds, you're beginning to see more and more people perceiving some kind of delay. Right? Around 100 milliseconds, basically nobody, nearly nobody is saying anymore that this is immediate, and most people perceive the delay that you guys also saw. And if you then were on to go on further all the way to 200 milliseconds and around like 150, 200 milliseconds, basically everybody says these things are no longer even connected. They're basically just two things happening one after the other. And this is not, as I said, not constant, of course. You can see here people decide differently. It'll also depend, for example, on how intense the contrast of the signal is that you're seeing. So seeing this in white on black, for example, means that you are able to see smaller differences, smaller delays, well, than if it was like in light gray on dark gray, for example. So why is this important? Because if we know that our perception time is around 100 milliseconds, right, then this explains a lot. For example, it explains why movies are running at the frames that they have. The movies are typically being played at least 24 frames a second. According to this number, we would say, well, 10 frames a second should be enough, right, to merge individual images into one continuous sensation, right? If you put images out fast enough, then it's going to seem like a continuous movie. But if we only go for 10 frames a second, there's going to still be people who perceive basically individual frames, like the faster reaction people at this point. So that's why we're kind of over achieving with movie frame rates of 24 frames or 30 frames a second, where we can be sure that for everybody in the room, it's going to merge into a continuous perception. So that explains animation rates, because the middle person, like middleman, as they call it in the original article, basically has these 10 frames a second, but faster people are going to need a faster frame rate. The other thing that this also explains is we now know that there is a maximum delay before causality breaks down. And as soon as we go basically well over 50 and enter the sort of 100 milliseconds, basically the idea that things are still happening with a cause and effect relationship is breaking down. And we notice the delays, and it shortens with intensity, right? So if there is actually high contrast, for example, these numbers are lower. And this is important because let's take, a physical thing. Like, for example, if I were to push this button here on this remote, like this physical button here, the moment I push it, I feel the physical button pushing. And if there was, and there's no delay in the physical action of pressing this button. And this button just closes a little circuit and it turns on the green dot. So that happens without any delay, right? This is how the physical world around us works. It has no latency, right? And so if you now build a computer interface, like you put a push button in an application, and the user presses the push button, and it's supposed to invert maybe to show that it was pushed, and you wait longer than 100 milliseconds doing that because your software is busy doing something else, that's not going to feel real anymore. Right? It's going to immediately feel sticky, slowish, something is going on. It's not going to have an authentic feeling, and users are going to start feeling uncomfortable using that interface and are going to feel like something is off or something is broken maybe. All right, so that takes care of the perceptual processor. Now we're going to move on to the next one, the cognitive processor. And for that, we're going to do another experiment. So this is the next experiment. As a group of two, which you guys have already formed, one of you folks will take the sheet that you have and read out a random sequence of 5 digits from that sheet, okay, to the other person. And then, so P1, the reader reads out these 5 digits. Then the listener is the person that we're testing, right? he counts backwards aloud from 50, right? Just to basically, keep their mind busy with something. Then the reader will ask the listener another question, like, what did you have for dinner 3 days ago? Something that also requires cognitive effort, right? And then you ask the reader asks the listener to write down the numbers that they still remember of those 5 digits. Okay? Once you're done with that, you switch roles and repeat this with 9 digits. Okay? And once you're done with that, you switch roles once more, and you read the entire sequence to your partner, stop at some random point, and ask them at that moment to repeat back as many digits as they can. I would like to know, first of all, the first round, 5 digits to remember. If your group, right, you're a team, right? We're not going to pick on anybody individually. So if you in a team manage to do the 5 digits, recall all of the 5 digits correctly, and can you both raise your hand? Okay. Okay, yeah, not everybody did managed to do the 5 digits. That's okay. It's, I know it's early and there's lots of, start of semester parties. So then we did 9 digits. If your team managed to, remember the 9 digits correctly, then raise your hand. Okay, we got 1, 2, 3. Yeah, so write down their names. We're going to hire them as Heavies, right? Yeah, so that's quite a feat. And there's a lot of noise in this experiment, right? Obviously. So, did everybody do it exactly the same way? Probably not. But what you should notice here is that, 5 digits seems to be doable, right? Even if you get a little bit distracted with other things, it seems that those 5 digits can stick around somewhere in your head. Whereas with the 9 digits, yeah, that's just too much, right? That would really require a learning effort, right? You would need to hear them more than once and really be able to recall this. So the last experiment we did was, how many digits can people remember? So what we're going to try is, again, do this as a team, right? So both people show up their hands. If your team managed to remember the very last digit, then raise your hand. That should be at least the very last one. At least the very last one. That should be everyone. Am I? So everybody should be able to recall at least 1 digit, right, from that. Come on. Come on. I'm working with you here. Hey, 2 digits. Who managed to do 2 digits or more? Or more? We're going to gradually see hands drop off, right? 3 or more. Who can do 4 or more? 5. 6. Hands are going down. 7. Okay. Oh, Marcel, really. That's why I hired him as a PhD student. All right. So as you can see, that was a tough one, right? Because you had no time to even repeat it back in your head as you did with the first ones. It was basically like constantly overloading your memory, short-term memory, flushing the pipe basically with new information, and then it's like, now I need you to recall what you just heard, right? So there we can clearly see there's something going on here around this number of items, right? And what's going on here is that we're now taking a look at the cognitive system. And lots of these, by the way, if you got less than 5, don't take it personally. You just may not be in a good condition today. And so that's okay. So what you observe when you do this with lots of people and lots of studies is that we can sort of differentiate 2 kinds of memory. The one is called working memory, and that's the one where you keep things around as you interact, as you think about it, as you work with it for the moment, right? And that working memory has a fairly limited capacity. The capacity is given with something like 7 chunks, although this can also vary. This other number here, the lower number, refers to how much capacity you have if you constantly flood it with new information. What's more interesting here is that the half-life of this memory is also limited. So if we ask people to remember things for longer and longer periods of time, you will see that your likelihood of still recalling something goes down. And so the half-life of information in working memory is somewhere around if it's only one chunk, I'm asking you to remember one piece of information, like one number, for example, then it will be around 70 seconds maybe. But if I'm asking you to remember 3 things, like 3 random numbers, then that actually, again, goes down to about 7 seconds, after which you have a 50% chance of still being able to recall these. So this is a fairly complex model, but what I would like you to take away from this is, we can think of working memory as a storage area where we can put a small number of items, right? So if your user interface asks the user to remember 10 different commands, like in a command line environment right now, and then use them the next moment, it's going to be tricky, right? It's going to be tricky for people to do that. Unless, of course, you do learning, right? If the person is allowed to learn, to repeat it back to themselves and do a conscious effort of learning it, then, of course, you can actually be able to remember things much longer. Also, that puts stuff then into long-term memory. In long-term memory, 2 things to remember about this. Basically, capacity is infinite. At least we haven't been able to do any experiments that would put a clear number on the limit of what a human can remember. And also, the half-life is basically infinite, right? You probably still remember some things from your childhood, as long as it's been a memory that has been deeply ingrained and has been used and maybe referred to back a lot. This stuff is not going to go away. Now, of course, infinite capacity, infinite half-life would be really nice for the final exam, right? So in practice, things work a little differently. It depends on how well you train yourself and how often you recall these things, how much these connections basically get used. So chunks, when I say chunk of information, what does that mean? It really depends on the user and the task. A chunk could be something like a single digit. That's a chunk of information. Or it could be a single word, like apple, right? Or whatever. But if you, for example, know a certain concept already, like, for example, if you've heard about a, I don't know, Boeing 747, right? Then 747 all of a sudden can be a single chunk because you already have that concept stored in your head, right? So the chunk will depend on, the size of a chunk will depend on how much you know about this area and at what level of granularity you already have a vocabulary that you can refer back to. I want to give you an example of what that means. Many years ago, I once had a guy he came into one of my classes because he was a colleague and friend, and he was able to recite back the number pi to like 1,000 digits or so. And he basically did that by chunking the information. Right? He wouldn't just remember the 1,000 digits individually, but he would put it together. If there was a sequence like 747, he would remember, Boeing 747 as one thing. Right? And he did, basically cluster the information into these larger chunks so that it was fewer chunks for him to remember. And then he actually made chunks out of chunks. He did this hierarchically so that he could unroll basically the 1,000 numbers of pi in a hierarchical fashion rather than having to remember 1,000 random digits, which nobody can unless you build yourself some kind of explanatory structure, to recall this stuff. Our working memory, if you remember that, there is a very famous paper from Miller from 1956. It's almost like 80 years old or so, 70 maybe. That's a paper that tells us that the capacity of our working memory is roughly 7 plus or minus 2 chunks. And the half-life, as I said, maybe around 73 seconds for one chunk in this experiment, 7 seconds for 3 chunks. And also, we have to sort of differentiate between visual and acoustic encoding, because when something comes in, it can come in through the eyes, right? I can see something and try to remember that. Or it can come in through the ears, and I can try to remember something I heard. And guess what? Visual has higher capacity, but a lower half-life. Why? Because audio is something that rolls out over time. So an audio message doesn't make sense if I just hear an instant of it, right? I need to actually, even to make sense of a sentence, I need to listen for some time and need to remember what was just being said, a few seconds ago. So the audio has a longer half-life, but not quite as high a capacity. the numbers are around like, you know, visual maybe 17 letters and 200 milliseconds of half-life, where audio has only 5 letters of capacity, but a longer half-life of about 1.5 seconds, roughly. And there's actually a newer result that's from the early 2000s, where somebody did many of these experiments again and is actually claiming that we are probably actually looking at an even lower capacity. And I don't think that's because people got more stupid or something. It's just that if you measure this, you know, very carefully, you may get different results. And it seems that the capacity of short-term memory is actually more around like 4 ± 1 chunks. So that's even less. And that is, you know, one of the things that you've all experienced this. You're supposed to type in an IBAN, right, for you know, sending money to somebody, right? Either it's one long string of digits, and you're like, oh, crap, right? It takes a long time to type in, or it's broken down into 4-digit groups, and it's super easy, right? Why is that? Well, because you look at a 4-digit group, you can immediately remember that in your short-term memory, no problem. It's clearly delineated with this little spaces, and so you type it in, and you look at the next one, and so on and so on. So the chunking, same thing with credit cards, right? That's also has the same feature, credit card numbers. Chunking it that way helps you to build these kinds of nuggets of information that you can hold on to in your short-term memory quite nicely. All right. So now, what about the processor? We've talked to memory a lot now, but what about the processor? The cognitive processor has also processing time. What does it do? Its task is to basically make, in the simplest way, you could say, associations or if-then decisions. So in that simple task we said, where the user has to, you know, look at the screen and the character appears and he needs to push a button, you know, just as a response to that, then at least the cognitive processor has to do that simple thing. He has to say, oh, a character appeared, push the button, right? It has to trigger that if. It's kind of like an if this then that in your brain, right? So it basically looks at something and reacts to that like a rule. That's the model for this model human processor at least. And so doing these derivations, these one-step decisions, these simple decisions, takes roughly a cycle time of the processor of 70 milliseconds. Long-term memory, I already said, infinite capacity, infinite half-life. How is stuff stored in long-term memory? Well, again, I'm not claiming anything on the level of, you know, brain, you know, medicine here, but we can imagine stuff being stored, at least for our engineering model, as associations. So a bit like a network of nodes and edges. And if, you know, for example, the concept of an apple isn't actually stored as an apple in there. It's just references to fruit and, I don't know, sweet and tart and about, you know, hand-sized, maybe a computer company, you know. So Apple is basically a concept for you that is defined in your brain and memorized in your brain by connections to other concepts. And again, we can get very philosophical here because that basically means that everything is just associations to other things. And so nothing really exists as a memory in your head. It's all just connections to other things. But, you know, knowing this actually explains a couple of, you know, behaviors. For example, you know, what do you do when you need to remember a really stupid number, right, that you cannot remember? What do you do? Like, I don't know, your passport number. Yeah? Yeah, you try to find a pattern, or maybe you come up with what we in German call the Eselsbrücke, right? You know, like a stupid little association that makes sense for that, you know, for that number to associate with. And so why do we do this? Because these associations then basically network that new thing into our brain with lots of, you know, ropes tied to it so that we can hold on to it and we can get back to it using those networked connections as access paths basically to that knowledge. Yeah. Yeah, so that's a wonderful example, and we will actually get back to number pads. They are an exciting technology. From a usability point of view, you can make lots of mistakes with them. But yes, for example, if I remember my credit card number or like the number I need to type in at the ATM, then I know it's a certain pattern. Not going to show it here, but it's a certain pattern that I have in my head, right? And I tried this once, and I was at an Italian ATM, and I typed in my number, and it didn't work. It turned out they had flipped the display around, and it was like the 789 was at the top rather than at the bottom, right? So so that can mess you up. So yeah, that's a good example. It's also using a different kind of memory in this case in order to memorize things. Final thing to remember about long-term memory is that it's a fast read, so you have quick read access to it, but it's a slow write, as we all know from trying to learn stuff, right? Learning is writing things into long-term memory, and that takes effort and time. There's also a maximum speed at which we can remember chunks of information. With a single pass, it takes about 7 seconds again per chunk of learning things. So you cannot cram things in. You cannot write to your long-term memory at arbitrary fast speeds. It has a certain maximum speed. Again, of course, highly variant between people. So that takes care of the perception. So you see something on the screen. The eye saccades, maybe reading something, or maybe just reacting to a simple thing takes. First of all, you need to realize it in your eye. Basically, your perceptual processor needs to process the image. It takes about 100 milliseconds. Then it gets stored. It actually gets stored in the visual or auditory image store. These are parts of the working memory that we haven't talked about yet. They are the ones where the information is being stored in a physical representation. So like the digit 1 would be stored literally as the shape of black on white pixels, if you want, right? It's a pixel image if you want to think about it that way. It hasn't been interpreted yet. And then your long-term and your near-cognitive processor goes ahead and actually takes that information and says, oh, is that a letter 1? Oh, yes, it is. I'm supposed to press that button, right? So basically, the storage is, first of all, physical and then gets converted into semantic storage, for sure in long-term memory, right, where it's stored via these associations. Now, what's left is the question of the motor processor. And that's the most fun part of in-class experiment. We're going to do a couple in-class experiments around your motor systems, folks. First thing I want you to do is get out a pencil, and take another look at your little sheet that you have in front of you. And I want you to draw strokes between those lines. I'm going to show you what that means. It's supposed to roughly look like this, right? I want you to do this. So try to reach both lines, but not go crazy over them. Try to basically turn around at the ends, but go as fast as you can otherwise. And do this for exactly 5 seconds. And I will time you all for 5 seconds so that we all have the same data here. Are you ready? Get your paper out. Got your pen there? I'm going to count you in with ready, set, go, and then you do 5 seconds of wiggling back and forth between the top and bottom line. Ready, set, go. And stop. All right, wonderful. Now, what you need to do is you now need to count reversals. What I mean by this is you count these numbers, the number of turnaround points at the top. Guess what? You don't need to count the ones at the bottom as well because, right? Okay. So do a count of that. All right. So you should have a number here. And let's say, just for the sake of argument, you got maybe 34 reversals. That would mean that you have, at the top, right? That means that you have 68 total reversals, correct? If that's the case, then you can actually figure out how many milliseconds you used for each reversal, right? You just basically take your 5 seconds and you divide them by the total number of reversals that you did. So just do that calculation in your head real quick. So you're basically doing this. Sorry, oops. There we go. And we should end up with a number here. Maybe we can get a few ideas on how many milliseconds per reversal did you use? I'm going to ask just a couple folks. Do you have a number? 100. You, yeah. Okay, 102 and 3. How about white T-shirt over there? Okay, yeah, 95 one direction. Yeah, each reversal, right? Each turnaround, basically getting from one end to the other, right? That time basically is what we're looking at. Any other numbers? Let's hear it maybe from right there. Green shirt. Yep. Around 100. Okay. Good. Right. So that should be that's in the order of what we would be expecting. If we do this with lots of people and maybe a little bit more of a controlled lab setting, then we end up finding that it's roughly around like 70 to maybe more milliseconds per reversal. And what you're doing there is basically you are checking how fast your motor system can send commands of turning around, right? Because you were going as fast as you could, so your speed was basically limited by how fast can I do these turnarounds. And so we end up with a number 70, 100 milliseconds. Doesn't matter too much if we nail it completely. Now comes a more interesting one. You now need to count the, basically take the bottom of your turnarounds and draw this line. This line connects all the bottom turning points, basically. Right? So you're drawing the contour of your bottom turning points now. And again, I want you to then count the number of those corrections too. Right? So now you're going to again go in, and the yellow crosses here show how often does this red line actually have an upper turning point? How often does it change direction on the top? Okay? And then you take that again, and in this case, for example, this would be 10 corrections at the top, so that would translate into 20 corrections total, right? Do that as well, and that should give you another number, and then take the 5 seconds and divide by that number. And see how many milliseconds that is. All right, we're going to just, once you guys have figured that out, I'm just going to take maybe one row and ask you guys to give me your numbers just to get an impression. How about you folks here? Why don't you start with, and we go down the row here and hear your numbers. What did you end up as a cycle time for that? 38 reversals total. Okay. Next, we would like to hear the milliseconds that it takes you to do one of those. 131. Okay, that would be fairly fast.
You need to do 5,000 divided by your corrections.
Yes, exactly. 5,000. Thank you, Marcel. 5,000 divided by this, right? This total number of corrections. Okay. New number? 277. I love it. Yes. 250. Good. Okay. I'm going to stop there. These numbers are so great, we're not going to hear any more. We are ending up with a number that is on the order of 200 to 300 milliseconds here. What is that? Well, as you are doing this, and basically your motor system is doing these wiggles, you are not controlling these wiggles consciously, right? You're not actually having a closed loop at looking at your finger, oh, I've reached the top, now I need to tell my finger to turn on. That's not what's happening. It's happening much faster than that. But as you do this, what you do see with your eye is, oh, my lines are getting too long. I need to correct, I need to make shorter movements. And that's a closed loop that goes all the way through perceptual, cognitive, and motor processor. So while each individual wiggle back and forth is only the motor processor cycle time, around 70 milliseconds. Here we had a slightly higher number. The corrections, this contour of corrections, when you are turning, when you are changing direction, like getting larger or getting smaller, when you make those corrections, is actually going to be on the order of 240, 280 milliseconds maybe. And that is your complete visual, or I should say perceptual plus cognitive plus motor processor all together. Does that make sense? Right? Because you're making a movement that, your lines are becoming too long. You see that, takes 100 milliseconds. Your brain says, got to make shorter lines. That's the cognitive processor, and your motor processor then reacts to that correction. And that's the full cycle in your system. Okay, so what we figure out is basically this is the motor processor open loop, right? Just basically making your finger wiggle at 70 milliseconds cycle time. And that's the cycle time of the motor processor. This is how fast the motor processor can do something all by itself. But, and that's the average time between each reversal, right? That's where this comes in. But if we take the closed loop, then it's actually, you looking at this stuff, the perceptual processor saying, oh, this is too long. Then your cognitive processor says, all right, let's make these lines shorter. And the motor processor needs to react to that as well. And that takes 240 milliseconds on average in a large population, right? So that's why this is the average time between each correction. Great. So that should help us figure this out. And this answers a very fundamental question. It says, if the light switches on the screen, if like a character or like a symbol appears on the screen, and I'm immediately supposed to press a button as soon as that happens, I now know that this will take, on average, right, with large variance between people and situations, but it will take, on average, about a quarter of a second. 240 milliseconds is the magic number here to remember, at least to have an idea, right? That's human reaction time. This is how fast I can react to an external stimulus by doing something. I'm not talking about finding that button to press, right? It's just literally telling my finger to push down on that button that I'm already hovering over, right? That's an important number to keep in mind. Now, since we're doing so many in-class exercises here, we're going to continue on with the last part. This is also a fun one. And this is called Fitts law. Because I just said my finger is already over that button, right, in this experiment that we just talked about, where we measured the 240 milliseconds. So I just need to push down. But what if my finger is not over that button? If I actually need to acquire that button, as we say, I need to acquire the target. I need to move my finger to that button. How long does that take? And we're going to learn something fascinating about people's ability to actually hit buttons with their fingers or click on things with their mouse while they're moving the mouse over a screen. That's why we're doing the next experiment, the tapping task. So first of all, if you are writing today with that expensive gold leaf fountain pen that your grandmother inherited you, don't use that for the next task, okay? So get a pen that you're not too concerned about bashing on the paper back and forth, because that's what we're going to be doing the next couple minutes. So get the handouts out that you have and take a look at these 3 sets of lines, okay? What I'd like you to do is to actually just tap between those 2 areas. So what that means is when I say go, right, I'll count you in again, and we'll do this for 10 seconds. I want you to basically put a dot into the left column and as quickly as possible move over to the right column and put a dot there. Move back to the left, right, okay? As fast as you can, but try to stay within the bounds, right? Or if you're slightly outside bounds, that's okay, but you want to actually, not just be all over the place. You want to stay essentially inside these bounds. And we're going to do this with all these 3 measurements. We're going to just start with the 4 centimeter one, the first one at the top, and the 1 centimeter gap, okay? So take a look at that, get your pen ready, and I'm going to count you in for 10 seconds. Hold on.
So, it should be about the goods. So basically, the interesting part that we can focus on is the part on the bottom. That's the interesting part that we are now looking on. And just to go through what these numbers are, so basically on this side here, we have the distance here, so how far apart these things were. And so basically the distance increases when we go from top to bottom. And on the top here, we have the width of the target. So how narrow basically the targets were. And now we're going to have a look at that and see whether we can derive a formula based on this, how we can maybe model this in the future. And what we basically see here is distance should basically be quite logical, right? So the further we get, we see an increase in the distance. So we first see that we have 24, then we have 45, and then we have 56. So we see increase in distance, increase in time. So basically our goal is that in the end we want to have the time it takes you to basically go from the first point to your target. So let's start with this. So we are interested in time. And we now know that it basically increases if we increase the distance. If we look at the width of it, so the top part here, we can now think about, okay, with increasing width, basically the target gets wider, so it will probably easier to hit it. Right? Smaller target, hard to hit, bigger target, easier to hit. And then we can see this again. So we see that first, with a small target, it takes you longer time because you're basically aiming and you're correcting mid-air while you're approaching the target. And with increasing width of the target, we see that the time decreases. So we go from 4.2 to 3.3 to 2.5. So now again, we know that this is basically the inverse of that. And this is basically already the interesting number. So we know that, again, we have a time that is equal to the distance divided by the width. Now we can basically see, okay, we could see it on the graph. So the graph doesn't really look like we expect it to be. It should look something like this here.
Yeah, I think the curve is a little flat in this.
Yeah, I mean,
view.
it goes a little bit steep here, and then it goes a little steep there. So it's not like this. But you can also look at the numbers and kind of see we double the number each time. So we're going from here to here. We double it, same goes on the bottom here, we double the number again. But the numbers do not double. So can you imagine what kind of function that is? Is it linear, exponential, something else?
Something else.
What is the third usual function that we have? Yes?
Logarithmic?
Yes! It's obviously a logarithmic graph. So we put a logarithm in front of it. And now basically, a little bit to the history of this law. This law basically takes signal modulation. So basically it comes from, okay, can we kind of take what we know about how signals are processed and kind of compare this to how the human might work in the end. And therefore Fitz said that basically we model the information that we have here in bits. So bits either being 1 or 2, 1 or 0, we have here the logarithm to the base of 2. And then something that we cannot really see here, but it's not directly the distance, it is 2 times the distance, and that's basically the base of Fitz law. So this is what's called the index of difficulty of Fitz law, which we will learn a little bit more about later, and this is basically roughly how much time it takes you to hit a target from a certain point, so from a certain distance that you know that has a certain.
Cool. Thank you. So when Fitz did this experiment, this is also old, right? This was somewhere in the in the 50s. So he was interested in how to design things like airplane cockpits, so that if you had to be really fast about pushing a certain button, like to eject yourself out of a cockpit, where would you put that button, and how much of a difference does it make if that button is closer to you or farther away or bigger or smaller? And to figure that out, he did experiments very much like what we did here today, but just basically with with you going between two actually conductive plates. He literally used a conductive pen, metal pen and conductive plates because this was before everybody had computers. So he measured the timing between these things, and what he found was, interestingly, this is a typical result that he observed, was that as we double the distance, yes, the time increases, but it increases by a constant amount, and that's a logarithmic nature, right? Also, he realized that as we double the target width, time goes down, but also by a constant amount. So that's what suggested to him this logarithmic nature. And basically, he looked for a curve fit for his experimental data. And he did this with lots of different so-called indexes of difficulty. We today did 3 indexes of difficulty, if you want to say. If you take the index of difficulty to be the coefficient of the distance and the width, right? That right-hand term here, the log 2 of 2d divided by w, we will actually, if you basically take both distance and width and take them times 2, nothing should change, right? So what that means in an applied way is that if I take our experiment and just make everything bigger, right, like on a photocopier, just scale everything up, then the actual time to operate it doesn't change. That's important to remember, right? If you have an interface with a certain amount of, with certain sizes and distances between buttons, for example, and you just make everything bigger, it will not get any faster or slower to use. It will remain the same. So with these observations, Fitz found that the best curve fit he could find for his data was this original Fitz law formulation that we see down here. Like the positioning time is equal to some factor times log 2 of 2d divided by w. Now, what's this factor there? Well, this factor actually kind of models how fast your pointing device is. It's called the index of movement. Index of difficulty is defined by the task. It's the distance and width of your target, right? But the index of movement is defined by the device you use or the technique you use to select that target. Is it just your plain finger, or are you using a mouse on a screen, or maybe something else? So that index of movement is a factor that changes depending on what kind of device you're using. He did this with bare fingers, and that's why he was able to model these things. It looked kind of like this in his results. He said, all right, if I plot now the positioning time against this index of difficulty, like log 2 of 2d divided by w, then I actually get, and he was kind of like, doing, like Marcel, kind of eyeballing things a little, saying, this kind of actually looks more like a little bit like a linear relationship. Not quite. There seems to be some kind of curve in there, right? But a reasonable first approximation for the kind of data that he got was this linear model. And this said, okay, so if I have a linear relationship between the index of difficulty and the positioning time, then that means there needs to be a constant factor that basically leads from one to the other. And that constant factor is the slope of that line, and that slope of the line is the index of movement, right? So the more this line gets tilted up, basically the steeper the slope is, the higher is the index of movement, meaning that you have basically, as your index of difficulty goes up, the slower your the slower your technique is, right? The device you use. Why do we have 2 different kinds of dots in here? Well, this is already a plot of 2 different experimental conditions. One was with the distance of 2 inches, and the other one with the distance of ½ an inch, right? And you can see here, even though they are completely different experiments with different distances, by mapping them into this relationship 2d divided by w, they actually fell together on one line, and that was the big discovery that Fitz made. So what that means is that we actually had, Fitz actually had found a way to predict, just by knowing how far something is away and how big it is, and knowing what kind of technique you use to operate it. And back in the days, it was basically just finger on physical button, right? the mouse hadn't even been invented yet for another decade. So simple, just push a button with your finger. He was able to predict how long that would take. And that's great, right? Predictive models are the best, right? That's what you really want. You want a model that you can actually take and you can say, this is how this is going to turn out, this experiment. I know this from my model. And then you confirm it with the experimental data. And that's why Fitts' law became one of the most fundamental truths, if you like, about this like low-level technical design of interfaces when you really try to judge performance time of input techniques, of devices, etc. Fitts' law continues to be studied and expanded and researched to this day. But the curve fit, something's still off here, right? Something's still off. So this can be done a little better. And there's two steps that happened. A couple of years later, 1968, Welford said, actually, I have a better formulation that has a better curve fit, and it also starts addressing an issue. Because the issue is, if you look at the original formula, 2D divided by W, that becomes problematic, right? The moment that 2D becomes less than W, we have a value of less than 1 here. What does that mean for the logarithm? Becomes negative. Oops, we got negative execution times. Like, I reached the target before I start. That's pretty awesome, sort of, you know, Avenger-wise or Marvel-wise, but not something you want in a science paper. So something must be going on, right? So that basically says that as we approach this area here, we see there's already, you know, it's losing contact to the curve, and our formulation would actually be wrong, right? Because we're cutting through basically the into the negative space for positioning times if we just continued this line, and that would be wrong. And it cuts through there before we get to basically ID equals 0. So that's not good. That's why Welford corrected that, and he also found a better curve fit. And then later on, Shannon, whose name you've probably heard from, you know, information theory lectures, actually found an even better formulation. That formulation was so good in predicting performance and such a good curve fit that it was actually turned into part of the ISO standard that captures operation times based on Fitts' law, right? So it's still called Fitts' law because he was the guy who first discovered this relationship. But Shannon's formulation is the one that you'll find in the International Standards Organization documents on the topic. And he said, well, actually, if you add a whole number, like a +1 here, then this completely removes the issue of negative numbers, right? We got +1, so we're never going to be less than 1 here, obviously. So no negative logarithms. And it's also a better curve fit if you add not just a index of movement factor here, but you also add an absolute term to it, right? That gives you just a more general formula, so you have more ways to adjust for example, particular input devices. So in this version of Shannon, the index of movement is replaced by both a constant factor that's added here and a linear factor here, and or a constant term, I should say, and a linear factor here. And these two are depending on the input device and usually need to be determined experimentally. But if you don't have an experiment, or you just want a quick and dirty estimate that is pretty close to what you would get with, you know, your bare hand, then actually using 100 milliseconds for the index of movement, or for B here in this case, and using a 0 additional term actually gets you a pretty good fit. All right, so that is a wonderful resolution of the whole formula. So we avoid the fact that we're entering, you know, negative space here with D less than W half, which, by the way, is an interesting moment. You know when that is? When does that happen? If you think about what you're doing with Fitts' law, what is the moment where the original Fitts' law turns negative? Yeah? Yeah, when you are starting your approach already on the button, basically, right? When you're over the button already, but you're not yet in the middle of the button where you're trying to go, in the middle of the target, but you're already at the edge of the target. You've started entering the area basically above the target, then it becomes negative, and that's basically not good. So Welford and ultimately and Shannon did these corrections, and these turned out to be better curve fits. We should probably, by the way, get back the a little graphic that shows the distance and width in a graph, indicating where these are. So now a word on target width. Target width is something that needs a little bit extra consideration. So if you take this orange box here, right, let's say that's your target, right? That's a typical button in a UI. Does this box have constant width or not? No, why not? Yeah. Exactly. Yeah. So, you know, approaching it from these 3 points makes a huge difference, right? Here it's pretty wide when I come from here. Here it's you know, very narrow, and here it's actually something sort of in between, right? The diagonal. This is important to realize, and you could try this out for yourself. If you are asked to hit a target at a certain distance, right? Let's say I'm supposed to hit this target. It's pretty easy to hit it sideways, right? You're not going to aim to the left or to the right of it, right? You're not stupid. But it's actually hard not to overshoot or undershoot, right? So this is where the task gets difficult. The distance in the direction of movement, the width in the direction of movement is the one that determines the difficulty of the task. Because sideways, we have plenty of time to make fine corrections all the way through. We're not going to hit, you know, hit next to the left or the right of the target, but we are going to over or undershoot simply because that is the velocity vector with the largest, you know, amount where the finger is traveling fast, and so it's easy to overshoot or undershoot. All right, so we want basically you know, to understand that, you know, targets are actually different size based on from which direction you are coming. And what that means is also that if targets are really narrow, they're really hard to hit, right? And what's really narrow from where you're typically coming? A menu bar. And that is why if you take a look at a typical design of a, wait a minute, where's the, there it is. You know, if you take a typical look at this here, like there's a menu bar up here, and you're supposed to select these things, right, coming up from somewhere down here, right? I'm doing stuff, and now I'm trying to hit one of those menu items. This is actually pretty narrow, right? And maybe next time you use one of those interfaces, try to observe yourself as you're trying to acquire these targets. You will find yourself overshooting, correcting, going back, etc. This is one of the reasons why this happened, of course, way back in the 80s, but why folks designing the Mac user interface went for a different solution and put the menu bar at the very top. Now, that menu bar is no bigger than the one on Windows, but it's at the edge of the screen. And that has a very interesting effect. If you put something on the edge of the screen, how wide is it in terms of the target width? Yeah? Exactly. It's infinite because you can hit the edge at any velocity you like. Your mouse pointer is going to stop at that edge, and when you then, you know, just go there like crazy and you click, you're always going to hit, you know, that button. So probably the worst placement you could do if you're like, you know, the interface designer from hell, then you make all your menu bars right at the edge of the screen, so really far away, but you move it 1 pixel down, right? So that people, you know, never be able to hit it. And I've seen those designs, right? This sometimes actually does appear. So remember that, you know, edges of the screen are really fast to reach, although they are very far away from the statistical average of where your mouse might be when you start, right? But because I can go up there at any speed I want, they're easy to hit. And of course, the corners are super easy to hit. That's why oftentimes you've got things like, you know, turn on the screensaver as shortcuts in those corners. Just throw your mouse up there, and it's going to, you know, hit one or the other edge and then drift into the corner, and that's where you are. Right? So these are super easy to reach. We'll talk more about good things we can do with Fitts Law in the lab. I think there's more stuff coming up. But we've got one exercise for you guys, and that's the last one I'm going to bother you with before we wrap up for today. But I want you guys to do this. So this is a task. You are a mobile phone designer, like maybe a smartphone interface, and you've got your number keypad down here, and you've got the dial button, right? So people are entering a number, and then once they've entered the number, on average, they are somewhere over the 5 key, right, let's say, and then they have to move to this call button, right? So somebody says, hey, our call button is currently 30 millimeters away from the number pad's center, right? It's this call button up here. What if we moved this call button? Are you sure, by the way, with 2 by 2 millimeters? Is that, or is it typo? Okay, all right.
Very small.
It's a very tiny call button to make it easy for you guys to do the math, okay? So what if we moved our call button up from that area down to this area? What would that do? Figure out how much faster it gets. Do a little bit of math. It's like in school. And remember, you can make your life easy by not trying to pull logarithms too early, right? Think about what you were doing. You're using this formulation, and we use 100 milliseconds per bit for B. We use 0 milliseconds for A. So you could calculate the two numbers, or you could think about what's the difference between the two, right? And that will make your calculations easier. You had a question? Yeah. Oh, okay, okay. So we'll hold on to that answer. We'll give everybody the chance to play with this. Here's the full calculation for the folks if you want to see the rollout. We basically just take the two positioning times for solution 1 and solution 2, being the further away and the closer one, and then we take the difference of those two, right? So by just inserting the formula for Shannon's version of Fitts law, we basically get the B times those two log terms in here, and then if we insert that again, we get, if you throw the numbers into it, this was 30 millimeters divided by the width of 2, and this was 14 millimeters divided by the width of 2. So we end up with basically log 2 of 16 minus log 2 of 8. And that's why you can thank Marcel for giving you easy numbers to work with. You don't need to think long about the log 2 of these two numbers. It's basically telling you that it's B times 4 bits minus 3 bits. So B being 100 milliseconds per bit means that we are left basically by an increase of difficulty or an improvement or a reduction of difficulty by 1 bit here in this case. And that, as you say correctly, basically means that the difference in execution times is going to be 100 milliseconds. So reality check here. Does that matter? If it's the phone, who calls people anyway, right, these days anymore? So if it's the phone and you call people maybe once a week, who cares? But if this is an operator's phone where they are doing this 8 hours a day, rapidly typing in numbers, or maybe like an emergency call center where every second counts, this will make an impact. Plus, not only does the thing get faster, but it also gets easier. We've literally reduced the index of difficulty of the task. It will be more comfortable for people to use. They will feel more competent doing this, make fewer mistakes, etc. So with that solution, basically, the each call that goes through is sped up. The connection is sped up by 100 milliseconds. Let me summarize before we wrap up. So what you have learned today, we are doing cool stuff, right? That was the most important first message. The second thing you should have taken away is HCI, human-computer interaction, is obviously about humans. It's obviously about computers, but it's also about the design process happening and the social context of interaction. Next up, we've talked about the CMN model, right? Cart, Moore, and Newell, the three guys who wrote the book, gave this the name of the model human processor. This model allows you to estimate reaction times and memory performance of humans. And that's an interesting thing to have. Without having to build a system, I can predict how people are going to likely react to it and how well they can remember some things. Secondly, if we want to actually precisely determine how long somebody needs to touch the target, we have Fitts law to thank for to be able to actually put a number to that. And that's a very relevant design guideline. We've learned some things like putting stuff at the edge of the screen, for example, is a really good idea. By the way, only works with the mouse. Doesn't work with your touch screen, right? Because your touch screen, your smartphone doesn't have an edge where your finger stops. So unfortunately, that design trick doesn't work on smartphones. What I also hope you've seen is that there are actually mathematical laws that govern some aspects of our perception, our memory, and movement, right? So we can create simple engineering mathematical models, even though they don't get anywhere near the truth of how our bodies and our minds work, but it's good enough to get some estimates to use in design work as engineers and researchers. What do you need to do now? Maybe the most important slide. You need to make sure that you register for the class in RTPH Online if you haven't already. Send your signed declaration of compliance via email to Ricarda and Marcel. If you have already sent us the doc, you don't need to do that again. Here's the email title and the file name, which is a highly complex parsable string that I'm sure you'll all work out. It's part of the test whether you're worthy of taking DIS1, whether you can figure that out. And finally, feel free to check out our other classes. In particular, iOS has a rapidly closing window for signing up. Of course, we would love to see you not only at DIS1, but also consider taking our follow-up classes once you've taken DIS1 in the upcoming semesters. And before the next lab on Tuesday, I want you to get the book by Don Norman. Get it on Amazon, get it at the local bookstore, get the ebook if you can't get it in time. But do get it and start taking a look at it. More importantly, though, because the stuff that we covered today is actually not something you'll find in Norman's book. This fundamental psychology stuff is not in Norman's book. So this is actually covered in the first chapter from Dix's book, Human-Computer Interaction. The chapter called The Human, pages 11 through 59. This is the one that we would like you to read. We will make the PDF for that available in Moodle so that you guys don't have to go out and buy the book just to read that chapter right now. Thanks, everybody, for listening, and I'm looking forward to seeing you again next time.
This content was provided by RWTH Aachen University.